Welcome to the Tufts Rocketry team's second design review for our Spaceport America Team Project Rocket, CARM. We had another one of these back in the fall in November, and we've learned a lot since then. We've gone to do a test flight since then, and we've made a lot of design changes. So we thought it was worth doing a second design review so we can basically go through all of that stuff and make sure we have it all fully fleshed out before we move on towards the competition. Next slide, please. Just some quick agenda today. Each of the sub-team leads will speak on their respective section that they've been working on for the project. We will be combining electrical, avionics, and telemetry into one section today, but that'll be relatively self-explanatory. Next, please. So, for some background on the team, if you're unfamiliar with the Tufts Rocketry team, we are a group of 48 Tufts students. We were founded in 2018. And we build and launch rockets. That's our thing. So we originally started out building individual rockets just for high power rocketry certifications. And now we've pivoted sort of to building these really big, complicated team rockets for competitions. And the competition we're going to this summer is the Spaceport America competition. So please. You have to click on that. But if you click off this, then as a team organization, we have the following sub-teams: mechanical, electrical, avionics and telemetry, propulsion, recovery, and the payload. We are not going to be addressing the payload today. They had their own critical design review just a couple of weeks ago. And so the heads of each of these sub-teams take charge of all the systems engineering and the logistics of the team. And that's us with the big rocket. Sorry, and that's one. Yeah, thanks. That's part of the mission. So yeah, the goals for this design review, we really want to apply the lessons we've learned over the past couple weeks, past couple months, and especially from the first test flight to sort of create a more robust system going forward and make sure we have a clear path to the competition this summer. As usually, we want to identify all the risks and lay out a good plan forward, good path forward to minimizing those risks, relatively standard CER stuff. And so we are hoping to do that today. For some overview on the project itself, CARM stands for CubeSat-Adorned Rocketry Masterpiece. It's been a fun little Tufts Rocketry team tradition that we name our team rockets after Tufts dining halls. So we'll be looking to carry that into the future as well. We started this project in spring of last year, and it's our entry to the Spaceport America competition. Now, what is that, you may ask? Next slide. The Spaceport America Cup is the world's largest intercollegiate rocketry competition, comprising, I believe, 153 teams from 88 countries. And they all compete in separate categories to try and loft a scientific payload of a specified weight to a certain height. So the category we're in is the 10K commercial off the shelf, or COTS. That means we're using a commercial solid motor to try and loft our 8.8 pound satellite to 10,000 feet, to as close to 10,000 feet in altitude as we possibly can. This satellite, CubeSat, it's about this big, 10 centimeters by 10 centimeters by 20 centimeters, is being built by the Tufts CubeSat project team, just sort of a sister project team to Rocketry. Next slide, please. So just a couple key definitions here. The biggest distinction is between COTS and SRAD. Again, COTS is something that we've bought and had it modified. SRAD is something that we've designed, built, researched, done ourselves. Next, please. There's a little bit of carryover from last year, but really not much. We had some pretty pictures, but the rocket we built last year, DUIC, was only about this tall. It was half the diameter, a tenth of the weight, much smaller in literally every sense. And so there's only so much carryover we have, and that's made this project incredibly difficult and also incredibly rewarding because of how far we've come. Next slide, please. So yeah, as most of you know, we had a first successful test flight just a couple of weeks ago up in St. Albans, Vermont. You can see the pictures, a couple of the pictures, one from actually both of them from GoPros placed around the rocket. It went up, had a nice stable ascent despite the high winds, deployed the drogue parachute at apogee, main parachute on the way down, and then landed with only minor cosmetic damage in a couple places. So as a validation of the airframe this was excellent. And we're very pleased. We're also, throughout the design review, going to be using this standardized risk matrix to track the risks and their potential impact on the Team Rocket project. And so every single sub-team has kind of copied this exact template, and that way we can kind of compare and contrast risks across sub-teams equally. Next, please. All right. Next up, quick overview of the systems engineering for the rocket. There's some higher level things before we move into sub-team specific stuff. So, quick overview of the vehicle. I actually didn't think to bring it here today. That would have been really cool to do. But we can do that next time. Anyways, it's almost 12 feet tall, weighs about 54, 55 pounds, completely empty of any fuel or motor hardware. And then once it's fully fueled up and we have the CubeSat, the payload in the airframe, it's projected to go to about 79 pounds. Now, that is also contingent on us getting the weight down for the second version that we are currently building. And then throughout the presentation, we refer to certain key parts. We have the booster, which is the aft airframe, it's the section with the fins, the forward airframe, which is the section with the pointy end, and then the avionics bay / switch bay is like the heart of the rocket. It's where all the flight computers are stored. It's where all the energetics, the explosives are stored for separating parachutes, and it's where the cameras are mounted to get some cool videos from the flight. Next, please. We did all our initial simulations and layout in a software called OpenRocket, and what this let us do was decide where we wanted to put components, what rough sizes we should make things, what geometries we should use for the fins, and then we can check how the center of gravity lines up for for all of those parts, and how the center of pressure lines up for the whole vehicle. And that way we can make sure that the vehicle is going to be passively stable on the way up. It doesn't have any sort of active guidance or control, so getting the stability margin to be within the proper window is key. The window here is greater than 1.5 or less than 6, and we are sitting at 2.78 with this version here. Quick idea of how the launch is going to go once we're at the competition. We put the rocket together, load the parachutes inside, integrate it, get everything ready, and then we put it on the pad. Once it's on the pad in vertical, we install the igniter, we arm the electronics, and we move about 1,000 feet away, because it is a very big and scary motor.
It's like 500.
Because it's an end motor, I believe it is 1,000. I'm not entirely sure. Sam can correct me on that.
End motor is 500, right? Yeah.
Right. Anyways, as soon as we hit the button, or the launch controller hits the button, the rocket will shoot up to about 10,000 feet, hopefully, where it will separate just above the fin section. It will deploy a relatively small parachute so that it falls quickly, but not too quickly. So we don't want it to float really far away. And then at about 1,500 feet, it'll deploy the main chute and come down for a nice soft landing and be recovered. So for our flight plans, we obviously had our first test flight a couple weeks ago. We're planning on having a second test flight on April 20th. That's the next available launch date up in St. Albans, Vermont, where we've been launching these things. And we will add a third test flight in May if we absolutely need to. This would be right after final exams, so that would be kind of a bit of a hassle. I'm going to try and avoid that if we can. We will see. All right, some quick overview on the parameters for the first test flight. This is actually the real flight data from one of the onboard altimeters. It is entirely pressure-based, so there's a little bit of a lag between this and the actual altitude, because this reads the pressure that equalizes through a tiny hole in the avionics bay. And as the rocket goes faster, there's a little bit of delay in the pressure equalization between the outside of the rocket and the inside of the rocket. I did some very preliminary smoothing on this. There's nothing fancy here. It's just a low pass filter at, I believe, 2 hertz. I don't actually remember which one I used. But anyways, point is, we follow our flight profile relatively closely. As you can see, we actually overperformed on apogee, on max speed, on time to max speed and max acceleration. So that points to either some slight deviations in the simulation, either with the setup of the weather, with the drag of the rocket, or it could be just the motor overperforming that standard amount. space. The second test flight will look relatively similar. We'll be flying on an M2045 motor up to about 6,100 feet. There's nothing particularly special about this. It will be noteworthy that we have still a relatively low rail exit velocity, which is the speed the rocket's going once it clears the launch rail. The higher rail exit velocity you have, the more stable your rocket will be, the better the chance you'll fly straight up. Our simulated rail exit velocity for this past flight was 63 feet per second, and it still flew relatively fine. And yeah, similar thing for the competition. Currently, we're simulated to 9,500 feet in apogee, and we expect that to drop a little bit depending on how the weight is looking for the upcoming version of the rocket that we want to continue building, or for the version that we have already flown. So we're working on that. There could be another 500 to 1,000 feet of unaccounted for altitude in here, because the thrust curve that OpenRocket uses to model this flight is based on sea level thrust. And we'll be starting our launch from 4,600 feet in elevation up in Mexico. And so historically, teams have seen their rockets overperform their simulations as we do get a little bit of thrust, a little bit more thrust at higher altitude. Next, please. And yeah, back to the stability analysis. ESRA, which is the organization that manages all the safety and logistics and official guidelines related to this competition, they require that our off-rail speed be 100 feet per second or higher. If not, we need to demonstrate stability with an actual flight test, which is what we ended up doing. So as you can see here, and Sam, I think I've sent you these pictures before, but it does help to see them side by side. We have a relatively straight and stable ascent from the rocket as it clears the pad, but it does turn slightly upwind as it gets to about 100 or 200 feet in the air. We're launching in relatively high winds at the upper limit of what we were allowed to do. But despite that, it still flew very nice. Also, as you can see, the rail itself was tilted a little bit. So that contributes to the angle we saw. But as you'll be able to see, or as you would be able to see from the videos, which I don't think we'll show today for the sake of time, as soon as it did that little turn there, it continued going in a straight line all the way up to average, which is fantastic. So, very happy to see that. All right, quick risk matrix for systems. This doesn't really mean anything without showing the risk table, please. Thank you. So yeah, biggest ones: schedule slip, flight failure, and insufficient funds. We've done our best to keep everything on track and have not had too major of a schedule slip that has impacted us. Although initially, if you'll recall from our last critical design review, we wanted to fly in December. But we've sort of rearranged our test flight program to be able to fly our first one in February, second one in April, and then add a third if we need. We haven't had a test flight failure so far, knock on wood, but if we do have a failure, we are building a second booster, which is a second aft section, the part with the fins, so that when we fly that on the next test flight, if for some reason that breaks beyond repair, then we'll still use the first one that we've already flown as a backup for the competition. So we just want to make sure we have the insurance of being able to fully test our systems without suddenly scrambling to build another rocket in 2 weeks. It's the most important thing for us is to actually fly the competition. Then there's a couple other risks which are also quite important. We can go over them if you'd like later, or if you have any specific questions about them. And yes, some things we're working on now. One of the biggest things that I've been most worried about is sort of increasing the autonomy of non-sub-team leads and finding and training future sub-team leads so that we can reduce the workload on all of us, and that we'll be in a good position if one of us is unable to complete everything they need to do for it. Then we want to also look at reducing the drag on the vehicle to get a little bit more performance out of it if it turns out that we're going to be significantly overweight, and that would hurt our apogee. Again, we are in this competition. We're in it to win it. We want to try and get as close to 10,000 as possible. So we don't want to sit back and take a 1,500 foot drop in altitude if there's something we can realistically reply. And yeah, we're also working to acquire the last set of funding to be able to fully fund all travel to and from the competition, which understandably is quite expensive since it's out in New Mexico. We are not in New Mexico. So we're still working on it. I have a slide on that a little bit further. Some big lessons learned from the first launch. We need to do more integration testing and practice before. We had quite a bit of trouble at the launch site putting things together at least efficiently. There's one thing when you're integrating the parachutes where we put it in and it didn't fit just right, and we had to pull it back out and refold things and then slide it in to make sure that the fit wasn't going to be jammed in there. And thankfully the deployment worked, it was worth it. But what we're going to be looking to do for the next test flight is sort of get everything done a little bit ahead of schedule and then spend more time learning how to use and operate the vehicle instead of leaving most of that to the launch day itself. And also once we have our student research and developed flight computers as well, we're going to want to do full integrated testing with those on board. All right, quick little zoomed in of the major Gantt chart that we had from last time. This is just the major issues remaining. There's not very much time, but last time we were able to essentially build the entire rocket in a little bit under 3 weeks. This time we'll have just over 4 weeks to do it, and a lot more people will be able to help who have more experience with the manufacturing and the design and the setup. So we will be on track to make that April 20th test flight. And we've learned so much already that it'll be just a lot easier from going forward. You'll see a couple of things up here. This booster 2 build, that's that upgraded fin section that we're trying to build to both minimize weight and make it a little bit more of a refined vehicle. The booster that we have, the fin section that we have, is built like a tank, and it holds up really well to everything. But it is so over designed to the point that it does hurt our performance a little bit. Right, next one please. And last slide, you couldn't have a project like this without funding. And we've been actually doing a really good job of making sure we're on track to get all the funding we need. We are a little bit off the mark given that it's a really big project, it is very expensive. And so we're currently working to sort of close that gap. We need another $3,200 to be sure we are at our target and fully funded. Thankfully though, we have everything we need to go all the way through to the test flight, and we have all the supplies needed for the competition flight itself, barring any major developments that we find something else we need to buy. And yeah, any excess funds that we get from our upcoming sponsorship crowdfunding rounds will be put towards facilitating launch site and competition travel for members either this year or in the future. All right, I believe that's all for systems. Also, I realized I probably should have introduced myself. I think this is the second time in a row I've done this. My name is Nico. I'm a junior. I'm a mechanical engineer. I'm the team leader of the Tufts Rocketry team, along with Bodhi. We've been doing this for the past 3 years. And yeah, this is like my biggest time commitment outside of school, probably including school as well. And I'm very proud of what we put together today and what everyone has done. So yeah, thank you. All right, Nick, take it away.
Well, I'll start by introducing myself. I'm Nick. I'm a senior mechanical engineer, and I'm also the head of the mechanical team. This is my first academic year, really being deeply involved in rocketry, but I'm very happy to be here. I've learned a lot. Excited to share what we can hopefully accomplish today. Okay, so our design overview, the key requirements remain largely the same as we discussed last time back in November. We want to not only create an airframe that's robust enough to survive the cycles of launching, potentially multiple times. We also want to create a platform that is suitable for the other teams, such as electrical, avionics, recovery, and propulsion teams, to integrate and do their own work. mechanical is the skeleton of the whole thing that all the other teams can contribute to. We also want to, of course, make sure we follow the competition rules. So here's just a quick overview. Up top is what we shared with you last time, and on the bottom is now the fully updated CAD model. You can see that huge amount of changes, primarily in the avionics bay region. That update. Go on.
Oh, sorry. Give me a second.
Yeah, so most of the CAD we'll be showing will have the obsolete version as of November, before we actually build anything, as well as the full color image on the left, which will be the current as of our most recent test flight. So the fin assembly, we have in red a smaller fiberglass motor tube that contains their motor, and we also have in gray are fiberglass sheets that were water jet and hand cut into shapes. So we have centering rings that align the fins, and we also have the fins themselves. And on the final rocket, the exterior airframe slides over this entire assembly. Essentially, it'll be it's epoxy along these lines as well as outside of the rocket for maximum rigidity.
Where is cursor? There's cursor. There you go.
There you go. So the thrust plate, we adopted a pretty different design. Originally, the design we were going for used mostly mechanical fasteners that would simply be attached by drilling holes at the very bottom of the fiberglass airframe. We were concerned that this would create undue stresses as you have an extremely small amount of fiberglass that's taking significant amounts of load. So we instead opted for this design, which has the downside of being much more difficult to manufacture. But it does mean that we don't actually require any machine screws or anything of that sort to actually fix it to the fiberglass airframe. This design is meant to maximize surface area with these grooves that were created on the lathe to essentially epoxy the entire thrust plate into the bottom of the rocket. Yeah. So the bulkheads, there are two of these on the rocket. They essentially serve to separate and, well, they serve to both separate and connect the section of the airframe. Also, the bulkhead in the aft section serves as a point to attach one of our rail buttons on that allows us to actually mount the rocket on and get launched. We also added this section of fiberglass tubing, which we call the bulkhead stop ring. Essentially, we have a chute pulling up on this U-bolt here. This whole thing will be concentrically encased within the airframe. If you can imagine a load pulling up here, this entire blue section is epoxy to the interior of the airframe, such that if a load is applied like this, it is secured really nicely. And then on our avionics bay, we also have two almost identical bulkheads that have 4 mounting points for all threads. We have 1/4-20 steel all threads that make up the core of our avionics bay. You'll see that in more detail later. It's a little hard to visualize right now. We also have more U-bolts to attach our main and drogue parachutes with, as well as black powder chargers and a CO2 canister, also called a Raptor, to help us deploy the parachute. So here's the avionics bay. Probably the most complicated single subsystem in the mechanical team's overview. So this old thing that we showed last semester was just a placeholder skeleton of an idea. This has also been by far the most interdisciplinary part of our project. We've been working together, avionics, electrical, and mechanical, to really make this come together. But we'll go into further detail. But essentially, it's as you can see, it has those 4 all threads going up and down it, and it's bookended at both ends by those avionics bay bulkheads. So essentially, and they have a tube kind of running the length of this entire thing. So the core of the avionics bay is the avionics sled, which is essentially our mounting point for all of our hardware that the electrical and avionics team is providing us. Essentially, what we've done is we've taken two sheets of, I believe, 6mm plywood and laser cut them to have all sorts of standoff mounting points for our student research and design and our commercial off-the-shelf flight computers. We also have mounting points for these batteries, the antenna, and more. And we also have these aluminum pieces that were made through a combination of using the water jet and a mill to actually affix them to the all threads. So the camera mount, we are planning on having two of these. We launched with one, but essentially these hold an upward facing and a downward facing camera, and it essentially, this curved section here is flush with the interior of the avionics bay, and this kind of rectangular section here sticks outside of it just barely, allowing for us to take some good footage of both our ascent and descent. And ideally, in the final iteration, we'll have two sets of these so that we have redundancy and multiple views. We also snuck a temperature sensor as it was the most convenient way to access free, relatively free stream air on our rocket without creating a whole separate assembly. There's also, you can kind of see them from the top here. The cameras each have their own independent circuit boards that are mounted conveniently on the backside there. So this is the payload adapter, or at least the tentative iteration of it. This is something that the CubeSat team has come up with, but I can explain it. Generally speaking, they have created in gray here essentially a frame, a structural frame made out of bent sheet metal. I believe they're using steel, and that kind of frames their CubeSat. And then for fit, it's not realistically going to be taking too much load. Ideally, they've created these identical pieces that they plan on 3D printing that give it a cylindrical cross section so that it can slot more nicely into the tube. And this is, although a work in progress, and we're going to be talking with them a lot on how to improve this and, come to a final design. Yes.
Speaking of work in progress, just a quick side note, Spencer, the power lead for CubeSat, realized that they are going to need more space to put more batteries. So the geometry of that may change to be able to do those.
So the bill of materials for the mechanical theme is largely just either epoxy and fiberglass materials or metalworking materials. So we have all sorts of, we use two types of epoxy. We used one epoxy resin that's meant for our fiberglass layup on top of our fins. We'll talk about that later. And we also use a type of epoxy paste that was useful for affixing things like a thrust plate or the fins. We also have plenty of fiberglass. We have G10 fiberglass sheets that we were able to cut into our fins and centering rings and other 2D geometries. And we also have plenty of G12 fiberglass tubing that serves all sorts of purposes. Basically anything that's a tube in the rocket is made from that. We use aluminum for most of for basically all of our machining purposes, just for ease of use, and we can use it for brake conveniently. Okay. So analysis. So one of the core requirements of the competition, and also just something important for rocketry in general, is to analyze fin flutter. And essentially what that means is, it is kind of what it sounds like. Does the fin flutter too much during launch? And that of course depends on your maximum speed, and it depends on the geometry of your fin very heavily, as well as the material characteristics of your fin. And we have a pretty comfortable factor of safety here. We're also considering, especially because Nico was kind of talking about how we want to trim down a little bit on our very overbuilt booster, we are potentially going to move towards slightly thinner fins for our next iteration, but we have a lot of room to work with essentially. And this is an equation used by almost everyone in the model rocketry and high power rocketry community. So for epoxy choices, we kind of opted for more mainstream options. There's a lot of, and you'll see this with the discussion of the epoxy paste. There's a lot of, kind of custom marketed towards rocketry epoxies. However, upon further investigation of their technical data sheets, talking to the manufacturers, we've bought all of our stuff from fiberglass just because of, reliable, nice data sheets that we get from them, fast lead times. They're honestly almost identical to, this one's almost identical to what's called aeropoxy, which was out of stock and also pretty difficult to find in general. But this is also recommended by Apogee, which is where we also buy a lot of our rocketry components from. So for the epoxy paste, it's a similar situation. We're replacing G5000 rocket epoxy, which is what the club has used in the past. It's actually strikingly similar how many material properties that these epoxies share with each other. Our biggest concern was essentially, as we discussed before, I was suspicious of this as well, even until we actually flew it. Are we going to, is essentially the thrust plate that we are only epoxying in there going to stay in there? And we have a reasonably comfortable factor of safety when we increased the length of the, increased the height of the thrust plate so that we had essentially more surface area to contact with the interior of the airframe. And essentially the calculation here is just a simple shear stress calculation. So then we also had to look at the avionics bay, which, as I said before, is primarily supported by those 1/4-20 all threads that we obtained from McMaster-Carr. Essentially, there's some calculations on the next slide that we can look at later. But essentially, we determined that we have a pretty large safety factor at our design load. Even if you said, put that load on each all thread, we would still have a very comfortable margin of safety. The primary analysis for the all threads, or really any nut on a threaded object, is essentially what fails first, the actual threads of the rod, or does the whole thing just tear apart in tension? And that just involves some analysis of the geometry, as well as understanding the material properties of the threaded rods that we use. And that is the math that Nico wrote out wonderfully. But essentially, it's just a stress calculation at the root of it. The most complicated part is just understanding that you have these two conflicting things about, will the threads fail or will the whole bolt fail? And then you also just have to understand the thread geometry. After that, it's more or less just a stress calculation. So we also did some FEA. I preferred ANSYS just because it's what I'm most familiar with, but any software would work well enough. We also performed some mesh analysis and geometry analysis to ensure that our results were at least somewhat trustworthy. Obviously, FEA should be only used as a supplementary tool. But we did see that essentially we didn't have any unrealistic stress concentrations or anything like that. And in all of our situations, we had a pretty comfortable factor of safety, even when accounting for maximum loads. What you see here is the avionics bay bulkhead. I did actually model most of the components that go in there because obviously if things are inserted through the holes, those affect how stress propagates through the material and how it deforms. And I just hid those for better visibility of the actual part we care about. But essentially, we were kind of limited by our computational power. As you can see, we kind of only got into the low 100,000s before the simulations took unreasonable amounts of time. But I still do feel relatively confident with the results that we got. There was nothing extremely alarming at all, even when analyzing for worst case scenarios. Yeah. Feature analysis. These are things that I kind of described in the first CDR a few months ago. But we've been a little limited by focusing mostly on actually getting the rocket done. However, there's lots of analysis that I think we could do. As Nico said before, a lot of our data depends on pressure sensors. And right now we essentially get pressure to equalize within the avionics bay where all the sensors are by drilling holes through the side of it using equations provided often by model rocketry. I guess if you do that, I can keep talking. Essentially, we use formulas provided by vendors to kind of get a best guess at what our hole size should be. However, it would be probably beneficial and also interesting to try and do, for example, a simulation to see how well our pressure actually equalizes within the avionics bay. Because obviously every avionics bay has different internal geometries and different sizing. So
This should work now. Oh, sorry. It should work now. Can someone say something?
Can someone on the Zoom say something?
It's good now.
All
Yeah,
right.
coming in loud and clear.
Thank you.
guys.
Thank
Now
you.
we got the
Amazing.
speakers working too.
Oh,
Cool.
fantastic. Okay, back to the slideshow. Yes, I'm moving out of the way. Yeah, thank you. Good enough. Yeah, that works. Other things that I'm running out of time here a little bit, so I'll just run through them quickly. But we could essentially do better analysis of drag because in Open Rocket, they don't really know our geometry. They don't really understand our geometry because it's not properly modeled in Open Rocket. We can also do more testing, especially of our composites, because it would be, we trust fiberglass somewhat, but it would be good to validate that ourselves, especially because our methods of usage might be slightly different from their test cases. And yeah. And also revisit our composites and try to get better estimates for those for their material properties. So into manufacturing. So the fin assembly, this was probably one of the more time-intensive ones. It essentially involved, our water jet is too small to actually cut our fins on there. It's very unfortunate. It was the right size to cut our centering rings, but not our fins. So that's me with a Dremel kind of just going at it very slowly on a downdraft table. And essentially it just took tons and tons of sanding, which all the people on the mechanical team are very familiar with, doing lots and lots of sanding. Thank you guys. But essentially we could get a pretty good finish on there, at least visually, using progressively higher grits of sandpaper and isopropyl. And then finally we would practice and then apply our composite layup. That's Nico applying it right down there. And the thrust plate, this took Nico and Bodhi probably what, like 25, 30 hours?
Yeah, probably.
Yeah, to turn because on the lathe, most of it was just hollowing out all that material because we got a 7-inch in diameter stock of aluminum, which is absolutely ridiculous to remove all of that on the lathe and bray. But thank you guys. And after that, the holes necessary to retain the rocket motor were milled, as well as the fin slots were milled, and other appropriate holes. And here are just more photos because of how beautiful it is and how much effort and time was put into it. It is beautiful. Yes. So the Advay bulkheads themselves were also not totally problem-free. Initially, we tried using the CNC machine in Bray, but ran into some issues concerning vibrations and holding it down essentially. So eventually the process was just switched to turning it on the lathe and then finishing the holes on the drill press, which was sufficient for our purposes in the end. Then the airframe bulkheads were a little simpler just because they're basically just discs. So they could be water jetted from stock and then just drilled on a drill press pretty easily and then bolted into the airframe. So these were thankfully a little bit more straightforward. And we are exploring potentially revisiting CNCing to do a little weight saving design on them and not just making them thick discs. But this was the best option given our constraints of timing mostly. And so the avionics bay, I cannot do this justice in the time that we have, but with the bulkheads created as described earlier, we also cut the avionics bay tube to size using a bandsaw. The sled and many of the parts on the sled were 3D printed or laser cut just for speed, and they're not structural, so it's sufficient to just use additive manufacturing. And then installing all sorts of hardware that will also be discussed in other sections more thoroughly because it's mostly electronics, avionics, and recovery. And we are going to refine this. First of all, how can we ensure that the electronics stay protected? And perhaps very importantly, how can we optimize the integration process for the electrical team so Bodhi does not get mad at me again? Because as you can imagine, it was a little bit difficult to assemble this with all those nuts and bolts on there. It took a while, to say the least. But we are looking to optimize it. For the camera mounts, we essentially just, these were also not structural, so we were able to just 3D print them. We installed some heat set inserts for mounting the PCBs and the temperature sensor. And then essentially we use this 3D printed stencil, if you will, and just went in very carefully with a Dremel. The Dremel was our best friend for most of the fiberglass working just because of the precision it allows, and the fact that you can do it pretty safely over the downdraft table while wearing PPE. And essentially just slowly cut it out and then sanded it down so that would be a pretty good fit. And you can see the fit that I had there. Yeah. Payload adapter. This is right now being handled by the CubeSat team. I wish I'd put a photo in there. I don't think I have any, but they are, I know right now they're assembling the sheet metal parts and testing things out. I know that they're not done with the design yet, but things are in progress. Regarding integration and assembly, things are a little bit less pressuring than last time because we have a booster and we have an airframe that is largely intact from our flight. That's a relief. So priority will essentially be refining the AV bay to allow for better progress for electrical and avionics teams, and just making things easy for them, optimizing use of space, because this AV bay was more or less just like, let's get it done, and let's get it done in a way that we can kind of change things a little last minute, but that comes at a loss of efficiency of space usage. And then CubeSat, I've been communicating with them lately about what their needs are. There's obviously a lot of very talented people on there, but we'll support them as needed. And also, Booster 2 will be constructed in parallel with our efforts this time. And this will also be a great thing for a lot of members of the mechanical team to become more experienced with independence and self-sufficiency, as Nico elaborated on earlier. The risk matrix, I'll really breeze by this because I know I'm really over time. Essentially, most of the risks are bad, very severe. There are not a lot of ways. Yeah, you can go to the next slide, Bodhi. There are not a lot of ways that this can fail just a little bit. Most of them come down essentially to it hit the ground really hard, or it did not withstand launch, or did not withstand parachute deploy. And most of the solutions to these, while there is obviously nuance there that is worth discussing, it can be mostly boiled down to, did we do good math and research and simulations behind it? And did we do our best practices for construction to create something robust? We can just skip past these. We'll share the slides later. So lessons learned from launch one, the revised design needs to prioritize ease of integration. I've said a million times, but it's very important, especially for on-site assembly. The AV bay also needs to, again, optimize the space efficiency. If you got a chance to look at it earlier, the sled actually doesn't take up all the space it could be taking. It'd probably be about 20% bigger, rough estimate. Also allow for better cable management with the new circuit board designs. So we'll design with those specific boards in mind, not just generic, like put the board here. And also, finally, we'll want to find methods to reduce the launch weight, as I somewhat elaborated before. So based on some of the math we did earlier, we can probably get away with thinner fins and also some weight-saving bulkheads. Yeah. Last slide, schedule of completion. Like I said, a lot of these things will have to be done in parallel, which will be interesting and very challenging, but it'll also be a great learning experience for a lot of the mechanical team to really get used to being independent and doing things on their own. And yeah, essentially we have 3 weeks of actual, good production time to get this done after break happens. But I'm confident we can get it done and, because we already have come so far. And that is it for me, I believe. Yeah, thank you all.
I can do this, man. It's kind of,
I can, you want me to
Yeah.
click?
I guess it's my turn.
Yes, it's your turn.
Yeah.
Thanks, Erica.
But yeah, I will follow up with you guys.
Thank you.
Send me your slides.
Yep.
For those who are still here, I'm Bodhi. I am the co-lead of the team and electrical lead. Daniel also be joining me for some of it. For electrical and avionics, we integrated them into one section to save time, as it's been a while already and we didn't want to make you stay ages. And also because it's the same physical system, and thus a lot of the things we're doing are working in tandem and testing in tandem and schedules in tandem, for more efficiently building it and more efficiently designing it, as we learned from the first time, always doing it, like, as we learned from the first CDR and doing them separately, we covered a lot of the same things anyway, so save time, we're going to do it in one. So basically, the general overall architecture, how we're designing this is we're going to have, it's actually slightly wrong, there's 2 cots, but that's besides the fact. We're gonna have 4 flight computers, not 3 on the slides, but we'll fix those before we send them out. But there's gonna be 4 flight computers, 2 of redundant versions of our own one, and then redundant versions of COTS. We're doing it this way, just so since we're not gonna be able to do as much testing as we wanted to in our own SRADs, we're gonna have a backup, our own and a backup one for our own. And then just in case neither of ours work, we're gonna have a backup and a backup with the COTS, just to be extra safe, just because we didn't get as much testing data as we wanted to on the SRAD boards. Go to the next slide. So the requirements of this is our goals are to deploy the recovery with the SRAD computer, track the telemetry data and store the telemetry data and send it back to the ground. So since with our board, our goal is to get extra data we wouldn't without either buying a relationship flight computer or using, and something we can't do with our current flight computers that we own, and we want to be able to design it so we can deploy the recovery. The requirements from the competitions, we must do GPS tracking, and we must use at least COTS for one system. So yeah. Okay. So the concept of operations, how this works, we discussed this is a drawing version of the nice pictures we had earlier. But pretty much we have inside, we have the 4 boards and the cameras and the sensors on the outside, which will be controlled by the SRAD flight computers. On each side, will wires going out to the deploy charges and wires going to the small charges in the recovery, which we talked about later. And then we also have motor 2 temperature sensors on the motor. There'll be wires that will be going along the recovery harnesses, and those will go down and be attached at the motor. Yeah. And on the ground, we'll have something that's like this, or have a laptop connected to the feather, which will be doing the GPS tracking, and then we're going to have a antenna that will be controlled and tracking, a directional antenna that will track the rocket and be controlled by another controller, so that it is always pointing at the rocket, so we make sure we have enough gain to get a signal from the rocket. This is a schematic of the thing. It is probably, I try to make it as big as possible because there's a lot going on. But I don't have a pointer, so I can't really point at things. So I guess I'll just like, can I use the mouse?
Yeah, sure.
Where's the mouse? Oh, wait.
Trackpad.
Okay, we'll use the trackpad. So I guess you just follow my mouse. Up here is where the power goes in. There'll be 2 for each SRAD board. There'll be 2 batteries attached to 2S. What's the specification? 18500, I think. Live batteries. Each of these will be, I skipped the page. Each of these will be going into full wave rectifiers, so we can have polarity protection, so it's very easy to switch them on site, so we're making sure we're gonna use polarity protection to make sure we don't do that on site. Then we have a voltage regulator set up here, and then down here we have a camera control circuit. This will just be turn off and on our cameras, and so that we can have more reliably get the footage from the flight. Here we have a buzzer to give us buzzes for continuity, and then it's on. Here we have our ejection charge circuit. Pretty much right here is the actual switch to turn it on, and the rest of this is just continuity checking, and has we're using LEDs to have continuity lights as well, and this circuit pretty much is just logic for those. And here are breakout board sensors. Here are we have our breakout board sensors. We're using all our sensors on breakout boards just to simplify things and simplify the design, especially since none of us are that experienced in circuit board design, and we wanted to keep it as simple as possible for the first time, so we can better learn how to design circuits. And yeah, and down here is a brownout capacitor that will in theory supply enough charge for each of the charges, so we don't have undervoltage to our processor when we fire the charges. And this is the PCB. It is all the traces are turned off, so you can't see where the traces are going, but this is how the PCB is designed. All the boards are attached on those places. They'll be attached with standoffs and pins, so that we can interchange breakout boards if one of them has a problem and we need to change it. And around the sides are going to be the bunch of screw terminals for all the different things we need to attach, like the batteries, the sensors that are not on the board itself, like the thermocouple of the motor and the temperature, and for the cameras and the camera batteries themselves. The cameras will be running on their own batteries, not the batteries we're going to use for the SAT computer, because cameras take a lot of power and we don't want that to be running on the same thing as our computer to prevent the battery from running out too fast. And you can talk about this part.
Okay, hello everybody. My name is Daniel. I'm the head of avionics and telemetry. I work closely with Bodhi on electronics, and while Bodhi works more so on the hardware side, I work on the software side. So what you see here is the general control flow of how the program is going to work. So on this side over here in the blue section, we have the CARM rocket computer, which is going to be located in the avionics bay. Essentially what it's doing is gathering data from all of these sensors over here, and the microcontroller that this is based on, which is the Feather, it collects them all and then bit packs them into, it essentially compresses the data and stores it to the SD card as a sort of black box system, and then it transmits it to the ground station, where it is received by our ground station Feather. It's connected via serial connection, which is just a wire from the Feather to a computer, to our parser, which then unpacks the data, saves it to a database, and is displayed on our dashboard. Next slide, please. Okay, so this monster of a diagram we have here is our state machine. It's a state diagram. So this acts mostly as a passive system for us to gauge what exactly is going on in the rocket at any given point in time. So these represent each of the states, what actions they'll be performing, and what data will be transmitted. We have state-based transmission to ensure that we're using as little power as possible prior to the flight. So over here, we're able to switch states from power on to launch ready, just to be able to do a quick check of what the sensors are reading, ensure that we don't need to calibrate them again. And from the moment that we detect a positive change in velocity and altitude, that's when we initiate launch mode, which is when we start going through these collection of states. And it's at when we reach apogee phase that this state machine stops becoming a passive system and becomes an active system, because immediately after we reach apogee, we want to attempt to deploy the drogue. And once we detect, well, not so much an increase in vertical acceleration, that meant that was supposed to be changed to some constant c. So once acceleration is greater than some constant c, it depends on what we're using, which simulation we're using. We would then, we would know that our drogue has been deployed, and then that's when we start detecting our altitude to figure out when we want to try and deploy the main. And once we are at or below the main deploy altitude, we would attempt to deploy it, and we would know that we deployed the main once we sense a sudden spike in vertical acceleration. So from there, our main is deployed. Once we reach an altitude of about less than 30 meters, we want to enable recovery mode, which is when we would start transmitting less data and mainly focus on transmitting our GPS coordinates.
There is an,
Please.
we can go back to that, there's an error. There is one error, that's where's mine, I think, the power on cannot go directly to the launch mode. It will require a switch in the middle there. That is missing from the state diagram. If the earlier that you saw, there was little dip switches, and one of those can be switched on to bypass from power on into launch ready instead of the button, just in case there's an error in transmission.
There's a little star I added there where I just say button refers to a specific, because I just say button refers to both the dashboard and a hardware button.
Then the, whatever, it doesn't matter.
We can fix that.
Yeah.
We fix later.
Alright.
We're gonna go quick over the parts. I didn't write all the specifications of the parts because I could talk about them for actually an hour and you would get the same thing out of it. So basically these are all the parts, what they all mean on the drawing back. They're not really that important for now. So we're just gonna go basic over the why I put everything into the circuit design. There's no I-2 squared pull-ups because there's built-in pull-ups from all the breakout boards that turn out to be how much power we actually need. The regulators improved from the last board. Since last time when we launched, we had the regulator shorted at the flight, so we improved our circuit there, so it has now more protection and also is smaller, so we can fit more things on the board. We added reverse polarity protection because we realized when we sorted our board at the site, we might do stupid things when we're in a rush. So we're preventing stupid things by adding full wave rectifiers. The charge circuit for the ejection charges is the MOSFET controlled by feathers and has a continuity circuit with a few NPN and PMP JTs that are used to control the LEDs. So we have physical, and we also go to the feather so we can have audio confirmation that we have continuity. This is the basic math for the Brownell capacitor, so it should theoretically give enough charge to the E-mesh until it lights up without having the battery to pull too much from the battery. The camera circuit can be turned off with a dip switch so that we have no cameras on there. We don't have that part of the circuit integrated at all, and we can not worry about it affecting anything else. And it uses MOSFET and digital input from the board, and then it can interface either to we can only interface with one of the cameras via software serial to turn it off. So each board will only be capable of turning off one, but it can turn on both. And then there's a piezo buzzer that uses PMW to control the sound, so we can tell when you have continuity and stuff. We can just basically go over it. The CARM radio system, we just basically have transmitting with a power of 20 decibels on a small swivel antenna inside the aft bay, and the ground station will have that's the current planned antenna. We might increase it to be a bigger antenna. And we'll use that to receive it from the ground, and it'll be mounted onto a tracking pad, so we always have it pointing at the rocket. Yeah, go on. This is the basic manufacturing order we have. We're going to we already prototyped on a breadboard. And we already designed the circuit board on KiCad, and will be ordered today probably. Assuming that there's no problems found in the speeding today. And then we'll outsource the making of it. And solder a single test board, and then we're going to run tests on that single test board and make sure everything works before we add anything to it or do anything with it. And then we're going to solder the remaining boards. We're going to probably solder 3 boards, in addition to the test board. And then we're going to add conformal coating on the outside of it to prevent them from shorting, during flight. And then we're going to put it onto the eBay slider. The integration, we're gonna put this in, we can skip this slide actually. This is the link budget for this telemetry that we discussed earlier. You can look at it. We don't really need to say much about it. So we have a margin of,
Decibel milliwatts. It essentially just says that we're going to receive data from 5 kilometers away. We're good to receive that kind of stuff. Yeah.
So testing, we're going to, basically for the test circuit board, we just test that all the sensors work. These are all the ways we're gonna test them. Basically, there's cross check of them and make sure they're reading data that makes sense. And then the most important thing is to test the range. So we're going to go to a very far area, such as a beach, and walk very far away from each other and see if we still get signal. We're gonna do state testing. So we're gonna do rigorously test to see if we can A, falsely trick it into changing a state, and B, make so it actually changes state when you want. Some of those is quite hard because without actually launching it, but we're going to do our best. But yeah, basically just do all the methods, these methods listed here to attempt to trick it and attempt to see how it can get tricked and how it cannot get tricked, so we can make sure that it will work as intended on the flight. Then we also the filters we're going to apply Kalman filters to the data so that we have smooth enough data that we can use to properly control the state machine. So basically, we're going to use data from previous flights and also data we found from very kind people on the internet that just share their flight data, and use those to train the data and make sure that later test the filters and make sure they actually work on real flight data. And then we'll actually trip our state machine as we want it to. We'll have deployment testing. We're going to probably do this once we integrated the rocket. We'll attach a shop vac to it and remove all the air from it to trick the barometer into testing if it will go off. We also can do this remotely without the shop vac. We haven't decided which one we're going to do yet, but we historically use the shop vac method. Yeah, and we're going to test to make sure it deploys correctly. Next one. And then we're going to do a passive flight test. Before we want to do anything with our SRAD flight computers, we want to fly them passively so we can assure the state machine works and that it doesn't falsely go off early or falsely go off late and goes off when we want it to. So we'll fly completely passively to make sure it works and make sure there's no misfires. And then we'll do a active flight test. This will probably be on a separate rocket, not CARM itself. And we'll test to see if it works again. We'll test it again, this time actually hooked up to the ejection charges to check that, make sure it actually works while flying and not just on the ground. Here's the risk images. You can go to the next slide. Pretty much the biggest risk is the state machine doesn't work, which is why we're going to test it on multiple flights, because that's the only way to make sure it works properly. And there's a lot of other smaller risks. The biggest issue is time on the test flights, and also lead times on buying PCB, and also reliability, which is why we're going to try to do it in multiple test flights if possible. This is a Gantt chart for completion, and basically our timeline of when we're going to do things and when we're going to finish them up. And yeah.
Hi, I'm Cisco. I'm a sophomore math major, and I'm both recovery and propulsion lead. So just very briefly, the general requirements from IREC for the competition are that we have both a dual deploy drogue and main chute. The drogue deploy at apogee and descend at below 75 or between 75 and 150 feet per second, and then the main has to deploy under 1,500 feet and have a descent speed of at most 30 feet per second. So our interfaces of the recovery team with mechanicals mainly in the bulkheads, the connection to the actual airframe of the chutes and the harnesses, And then also the shear pins connecting the sections of the airframe together. And then the U-bolts on the bulkhead and the quick links connecting everything together to the chutes. And then to avionics, we connect igniters to our energetics through the flight computers. And then we have the CO2 system is actually inside of the AV bay, which I will describe later. And so then the flight computers send a signal to our igniters. So the general concept of operations for the recovery system is at apogee about 10,000 feet, the drogue chute about 36 inches in diameter will deploy attached to a 25-foot harness to the aft airframe and 35 to the forward. And then at about 1,500 feet, subject to change, we will deploy the main, which is a 96-inch chute with 40, well, we have projected 40 feet and 10 feet, but this was changed on the flight test because we learned that in order to actually get the main chute out of the 10-foot of the forward airframe, we would need a much smaller harness. So we doubled up this harness and used a 5-foot harness instead of 10-foot. So we might continue with that. So in the test flight, we used a purely black powder charge to eject the parachutes, but in the actual flight and in the next test flight, we'll use compressed gas. This is what's called a Raptor system, and it's got a little bit of black powder here that sends a pin pushing into the compressed CO2 canister, thus rapidly expanding the gas, exploding, and separating the airframes. So this is the integration into the bulkhead. This is the that's from here over is the avionics bay. This is the bulkhead. I don't know if they can see that. Can you like
Didn't
come
see.
on?
Sorry.
Yeah.
You're on my.
Okay, I got it.
Yeah.
So where did it go?
Top left.
So
Thing
okay,
where-
I'll
It was just
describe
pointing.
it. So the CO2 system is actually inside of the avionics bay and attached to the bulkhead. On the other side, the Tinder Raptor and the black powder wells are on the other side of the bulkhead with the U-bolt on the side of either the forward airframe or the aft airframe, depending on which section it is, drogue or main. And this is actually wrong. I guess there'll be two COTS computers attached to the black powder well, and then the SRAD will be the primary computers attached to the primary deployment system of the CO2 compressed gas ejection system. And then, so the Raptor that we'll be using, this is sort of the diagram of how it works, or what it looks like. Not that important. This is how it will be attached to the bulkhead. There are 4 screws. And then, so yeah, like I said, the actual CO2 canister is inside of the avionics bay, and then we'll expand the gas outside to the compartment holding the chutes and the harness. So we will have the primary ejection system as the compressed gas, and then the backup redundant energetic is the compressed gas in that 1.5 inch black powder well.
Sorry, it takes a bit.
You're good. So sort of not that important, but we just have, I don't know, should I go over this?
No, it's not.
Yeah, it's not that important.
I think we can look and see if we're reducing any of these for weight, right?
Yes, we might use only 2 quick links instead of 4 quick links instead of 6.
Okay.
So sort of an analysis of the system, the black powder charge is produces a lot of heat, and the nylon harness is not really rated for extreme heat, so nor is the main parachute. So we have to make sure and protect that and cover it in a no-maxi protection blanket, and also there's a core protector attached specifically to the harness to the avionics bay bulkhead to protect from the heat, but hopefully only the the CO2 ejection will be deployed, or the CO2 energetics will be deployed before, the black powder, because for this next flight, hopefully, so that we don't have that heat against the harnesses. Then we also have analysis of this connection, the strength of the connection points and the quick links and all the links and the connection points of the U-bolts. And everything, all the connection points are rated for at least 3,000 pounds, except for we tested the sewn loops in the harness. The harness is a 11/16 inch diameter nylon harness or tubular harness. So I sewed a connection point of 6 inches of sewn parts of the nylon. So we tested that on a Instron machine, and that was rated to, that withheld at least 1,300 pounds, but that could be more. I feel like because I don't know, anyway.
For a bit more context,
Yeah.
I don't happen to have it in my pocket, but the harness like tore right at the point where it was clamped in the jaws. So we think it was just abrasion with the jaws and not the harness itself.
Yeah, I
right?
was gonna say that,
The
but
jaws are like heavily textured.
of the Instron machine, yeah. Anyway,
Sorry. Next slide.
yeah, next. So this is the data of the pull test. It went up to like 3,600. No, oh my gosh. 1,300 pound force.
Still a lot.
Yeah.
There we go.
So going forward, we have to repair the main chute because the black powder charge, or the black powder blast burned some holes in the main chute, which we'll have to repair during flight test when that happened. So we'll have to design and make a more protective heat protection system, and then integrate the Raptor system and connect it to light computers, and same with the VP wells into the avionics bay bulkhead. So the order of integration, connect everything, connect all the harnesses and the chutes together, fold the chutes, connect them to the bulkheads, and add the heat protection. Coil all the harnesses and connect all of the igniters to the energetics and the flight computers, and integrate with your pins. So testing, we have tested the ground, or on ground for the black powder wells. I'll talk more about that in a second. The flight test was a success, dual deploy, both drogue and main, deployed at expected altitudes. Next, we'll have to ground test the CO2 Raptor system and the flight test for that system. And we also have to test the deployment bag, because I was not, we did not use a deployment bag for the flight test because not enough research was, or the deployment bag was a bit more complicated than I had expected, and didn't research enough on how to actually use it. So we went without it. And we also need to figure out the new harness configuration. Nico. So for the ground test one, we tested the preliminary calculations for the mass of the black powder. And both of those for the drogue and the main worked very well with 4 and 6 shear pins respectively, 440 nylon shear pins. So we went with what we had calculated, and rounded up a little bit. So we ended up using 3 grams of black powder for the drogue and 6 for the main. But some things where we could have done better for the ground testing is for the main, we did not have the entire rocket assembled. We only had the forward airframe attached to avionics bay, pulled a vacuum through the Raptor plug in the av bay. which is why we didn't have the booster section attached. And then for the drogue, we actually did have the entire rocket assembled, and we pulled a vacuum through the keyholes for the flight computers. So if you go to the next slide, we don't have to, oh, they're not even there, okay. Never
Oh,
mind. Yeah, so this is what I mean. We pulled a vacuum, so the shop vac is attached to the hole in the bulkhead where the Raptor system would go. So we were not able to attach the booster section. And then, so that's what the right-hand side picture is, and then the left side is the test for the drogue, where we did have the whole rocket assembled, and the forward airframe was what was ejected. So next we'll have to test the compressed gas ejection. And upon research, it's estimated to be 5 times the mass of the black powder, so that's probably what we'll calculate to test on. Let me know if that's wrong, because I'm looking for advice on that. And then so we'll also need to test the drogue, or I mean the main being fully integrated. So when I talk about the burns that happen in the main chute, wait, can you like hover over that little dot? Like right under the mouse, it's not cooperating, but there's a burn in the main chute, and then as you can see on the left side, the chute deployed, both chutes deployed, and that's the rocket descending under main. So risk matrix, there's not a lot of really, well, the high risks are really high risks, but there's not a lot of them. Can you click? So main risks to consider are deployment system failing, or the main or drogue tearing upon deployment. And so things we have to still figure out is the deployment bag usage, and how to successfully get the main chute out of the forward airframe upon ejection. We, upon research, we could either use a smaller chute to actually pull the main outside with the smaller harness attached to the main. So we need to figure that out, and then also what altitude to actually deploy the main out. And I don't know if I said this, but in the main, or in the flight test that we just had, we deployed at 700 feet for a 3,600 altitude, or 3,600 foot altitude.
And how did that work out?
Just fine, perfect. Well, the calculations for that is I sort of scaled for the projected. I have 10,000 feet altitude, and I was going to use a 1,500 foot altitude for main ejection, and so I scaled. That's about 15% of the apogee, so 15% of 3,600. It's how I got the 700 foot. Actually, that's much. 700 feet is much higher than 15%. Just margin of error. So like I said, we still need to repair the main chute and figure out the deployment bag, ground test the CO2, and figure out the protection plan all before the next flight test in mid-April. I don't know why the repair of the main chute is there twice. You're on this.
Oh, I was gonna say, okay.
Yeah.
Real quick, Sam had some advice in the chat
Okay.
if you wanna
Yeah.
and ask questions about that. Thank you, Sam.
By abrasion during descent, do you mean the
So what I mean is during descent, it's really common for components to be, moving around a lot, and there's often a lot of twisting, especially before the main comes out. And so I'm just saying that if there's anything sharp anywhere near a line, it's something you need to prevent, because because it's much more likely the line's gonna get cut by something sharp rubbing against it than any other failure mode. So that's something you really have to watch for. Especially with the 10K flight where you're gonna be falling for a significant period of time under drogue.
Got it. Okay.
And then I think you also mentioned you wanted to shorten up the top segment a bit. I think that's right. It looked like you were still had the nose cone riding above the body, the sustainer, or I'm sorry, the booster. But you want to make sure that you have a good amount of distance, so there's very little chance that it could hit.
Yes. Yeah, that's what I preliminary calculated it so that the nose cone or the forward section wouldn't hit the booster or the ab bay, but you're right, I'll probably shorten it a bit more.
Yeah.
Perfect. Anything else?
The thing with I've had shoot skip burn holes ism before. It's tricky to put enough Kevlar in there to prevent it, but all I can say is those little holes won't make much of it, won't make any difference in shoot performance, but it's probably something that the safety testers at will probably want you to fix. But I've flown shoots with holes like that before, not a problem.
Okay, good to know. Thank you. Good to move on? Yep.
Yep.
Okay, so, for propulsion. Where's the mouse? There it is, okay. So we're using a 98mm diameter, for the competition and a 75mm diameter motor for the, both the testing. We're using Sub-Zeroni, COTS motors. And, okay. So the propellant is an ammonium perchlorate, never say that, composite propellant, and we're using Aeropack, for the COTS thrust plate. So I'm gonna talk about that in a second, so can you just, yeah. So for the, testing, first and second testing, we're using a Pro 75 6-grain motor. For the first test, we used the L2375 motor, which was only 4 grains, so we had to use 2 spacers, which worked perfectly fine. And then for the second test flight, we'll use the M2045 and we won't need spacers. And then for the actual competition, we'll use Pro 98, and that will be a 6-grain and 2600. So for motor retention, like Nick was talking about, this beautifully fabricated thrust plate is used, and then the motor is inserted and the motor retainer is screwed in over the thrust plate to retain the motor. Yeah, so thrust plate, oh my gosh. And then retention cap, beautifully manufactured. So the first test motor that we used was the L2375, performed beautifully. Yeah, actually overperformed. Next one, slightly higher thrust, M2045 motor, much higher, or almost double the burn time. And then the final competition will use an N2600 with a max thrust of 3000 newtons. So to actually assemble the motor, we prepare the grains. We learned that we need to sand the outside of the grains and the liner in order for everything to fit nicely. I know I'll talk about that in a second. But we do not epoxy the grains in to the liner. But we lubricate everything, integrate the nozzle, grains, and then into the casing and into the rocket. So the integration of the L2375 motor went not so smoothly. It did perform very well though. So some issues that we had with integration is that the first O-ring went in, and it was very tight because I believe it was possibly because the chamfering on the inner edge of the liner where we had inserted the grain was not done as well as it could have been. So it maybe scraped the grain or some like something was wedged in or something happened to make the grain not fit as perfectly as it could have. So what we did is we took the nozzle out against what the instructions had told us to do, and we integrated all of the grains vertically instead of horizontally as the instructions had said. And basically makeshift mallet, meaning hammer plus wood, because we do not have access to a mallet. And we hammered all of the grains in, which took a long time, and then into the liner. And then eventually we put the nozzle in, making sure that the grains were exactly lined with the nozzle. And then we next ran into an issue when we had no case wrench to tighten the nozzle closure or the closure. So what we end up doing is hammering the grains in little by little until we had it exactly lined up with the closure, like so that it was flush, the closure was flush with the liner, but not too tight. It was a long process, but it flew well. So, but we have learned our lesson. And we also, in putting the liner into the case, we put just a little bit of lubricant onto the liner. That was also a very tight fit, but we got it in. And we learned post-flight that putting only a little bit of lubricant ended up causing the liner to be bonded to the case, especially since we waited a little bit longer to actually get the liner and the motor out of the casing. So it is still currently stuck in the casing. We might use a blowtorch, heat, maybe acid to get it out. We're still working on that. Oh, and also it took 3 tries to actually ignite the motor. Because the supplied igniters, we think the power gen might have come off. There's some issue, but it ended up lighting. So the biggest issues, motor explode on ignition or during flight, and then also the simulated apogee is below the 10,000 foot target. We also have lower order risks in the motor casing being damaged or broken or lost, which did happen, which I'll explain later. Actually, no, I won't explain later. Upon getting the liner out, we sort of chipped the threads, and we also can't get the liner out, as I said. So we're working to fix that, but we have ordered a new liner or casing. And then motor doesn't properly unite on pad. That does happen as well, but. And then, so open issues, we'll still have to figure out how to effectively, quickly, efficiently assemble a high thrust motor. We have successfully done it, but none of those things were efficient. And then we ordered a case wrench and we ordered a new case. And the liner is still bonded into the case. We need to get that out.
Question on efficiency. How long did it take us to integrate the motor?
It took us 6 hours to integrate the motor.
It's a fun time.
So we need to, the case and also still has a lot of burnt phenolic and combustion materials on it. So we need to fully clean all of the threads, which is a very tedious task. Sometime in the near future. And attempt to salvage, meaning sand the threads to make sure to attempt to have it salvageable for like a flight in the future, even though we do have a motor coming, a case coming in the mail. We also need to do, for the next motor, the M2045, for the next flight test, we need to do a motor fit check. And sand liners to make sure that everything fits well, make sure that we actually chamfer the edge of the liner well. Try to make it under 6 hours of integration. And assemble the motor before the next test flight.
Yeah, Sam, do you have any specific advice on the propulsion stuff besides that?
So, I said in the chat, I like to use, there's a dry lube spray that I've used very successfully on, especially the inside of the case. That helps a lot with getting the liners in and out. And usually if you use it, if you use a good amount of it, it's the last Pro 75 I flew, the liner popped right out and it cleaned up very easily. So that usually works pretty well. I mean, did you use like super lube for lubing
We
when
did. Also, when you said it popped right out, did you take the liner out? Like, how soon after the flight did you take it out?
Actually, I had the last flight, I had the rocket got caught over a power line and I didn't get it out for like 3 or 4 days.
Okay, well,
Because they had to get someone to pull it down for me.
and then it came out well after using
Yeah,
the
it
dry
did.
spray. Okay, noted.
I mean, sometimes it could just be bad luck with it, but I think when I learned how to fly these motors, everyone recommended the dry lube, and I would highly recommend that. I can send you what the stuff I usually use. The other thing is there's a particular cleaner I've used when I've had particularly tough to clean motors. This stuff called CLP. It's like a spray and it's designed to be used for cleaning out gun barrels, but it works very nicely on motors. And that works pretty well. If stuff's stuck, the other thing is I have a brush that fits onto the end of a drill that I've used for cleaning out motors as well. The one thing you got to be really careful with is to not do anything that'll mess up the threads, because if the threads aren't biting well enough, then the motor's will come apart under pressure. So that's really critical.
So we did end up chipping the threads because we tried to chisel the liner out, and that ended up knocking the threads a bit. Do you think we shouldn't try to salvage those threads at all?
It's a risk, and it's I probably wouldn't, given that you're going to be putting it with a pretty expensive airframe, and losing that to save a motor casing is probably not worth it.
So you think we should retire that casing?
Probably, if there's any real damage to the metal underneath, I usually would say that.
Okay.
Yeah, I'm a big believer I'm willing to pay a little bit extra to make sure we save the cost of the entire rocket. So
Yeah. The other thing I would say is I do have if it's for this next test flight, I do have a Pro 75 wrench. Although frankly, it does make it easier. I mean, it's worth having.
Yeah, our problem was that we believed that it would, like, the purpose of having the wrench is that it would push the grains down as you screwed it, and we couldn't get a good enough grip to actually put that much force into the torque.
Yeah, you definitely should get one.
Yeah, it's coming in the mail. So we should order that. Anything else?
No, yeah, I think other than that, yeah, I'll send you the stuff I usually use for the lube and the cleaner. But yeah, usually, and the thing with the having it be hard to get the grains in, I mean, that has to do, a lot of that can have to do with humidity and everything, and it just, if the cardboard, if the stuff that the liner was bonded to, that there's like a cardboard that they bond the grains into, and if that gets a little bit damp, it can swell, and then it's hard to get it in the liner. The liner part, the part that's phenolic, you have to be careful with, because that's what's keeping your motor casing from melting. But the cardboard around the grains is just cardboard. It's just to shape it. So if that needs any sanding, that's not a big deal.
So it's better to sand the cardboard than it is to sand the phenolic.
Yes, absolutely. Because the cardboard's just going to burn up. It doesn't make any difference. Whereas the phenolic is what's keeping your liner, your motor from failing.
Also, so we ended up, the instruction said to integrate the nozzle before the grains and integrate the grains horizontally. But because we ended up having to put so much force and like essentially mallet them in, we took the nozzle out and integrated the grains vertically. Do you think that taking the nozzle out would cause an issue?
So no, I don't. I would point out that the fact that your motor succeeded, it probably means you did it okay. But in general, I've had trouble with it or I've had the nozzle pop out while I'm trying to put the grains in. I think the critical thing is that you get that, the critical thing is that you get and for the M, I'm gonna be with you anyways, but the critical thing is that, that the nozzle's all the way in the nozzle holder, so it's fully seated in the O-ring, because if that doesn't happen, you'll have a failure there. And that you need to get the nozzle and you need to have the nozzle nicely seated in the phenolic liner too. So the critical thing is that they're all seated the way they should be. The order is less critical.
Right. We were also considering at the end, like when we put the final grain in, hammering the grain in with the mallet, or no, with the nozzle attached. So hammering it in on top of the nozzle. Do you think that that would have been maybe more beneficial than it would have hurt the nozzle because it would have seated it in further? Or do you think it would have hurt the nozzle more?
I wouldn't be hammering in general. I mean, that's where I would rather push hard than hammer.
We had 5 people genuinely standing on top, not genuinely standing, but Bodie was sitting
And
on.
what was having trouble getting it in all the way, or getting the?
So the first grain was the issue because I think there was something like that. My belief is that the chamfering in the liner caused some bend in the cardboard, and then that caused so much like friction in the first grain. So then every grain that came after that, we just had to push harder and harder, and we couldn't even get the first grain in with like manpower.
I would have started by, number one, you could put them in from different directions if you take the nozzle out. And then the other thing is I would probably have sanded it more so that you didn't have that much friction.
Okay. I was against putting it in opposite directions because I was thinking that that would like, we wouldn't know for sure if there was a gap between that first grain and the other grains. So
You should be able to push. No, there's 2 things. One is there's supposed to be a little bit of space between the grains and the end of the phenolic. And if there's not, then you probably don't have them in all the way. And then the other thing is that, yeah, I mean, if it was really a significant gap, it would probably, you wouldn't have it lining up properly with the ends of the liners.
Thank you.
Yeah.
Yeah.
Thanks, Sam. That's really helpful. Really appreciate it. Yeah, real quick, just for the purposes of like, since we're recording this one, go through all of it. Just go through the next couple slides here. Just some acronyms and abbreviations for reference. There's these ones. There's those ones. There's probably more that I forgot. There's a lot of them. We use a lot of acronyms. And then we made some engineering drawings too of a lot of the parts, but we just didn't include them up in the mechanical section to try and save on some space and presentation time. So I'll just cycle through those a little bit. Hopefully they're visible to you guys. And yeah, this is just, it'll help us to make the parts when we have to make a couple more of them, if we need to make any replacements. And when we need to like delegate the manufacturing to members of the sub team who maybe didn't make the part. Sorry, didn't design the part themselves. And these are the parts from CubeSat, which they're taking care of manufacturing. And yeah, so that is our design review. If anyone has any questions, now would be a wonderful time. Does anyone have any questions?
I'll go, Nico. My questions won't be any very, this is Doug Mattson. Yeah, my questions won't be as helpful as Sam's. But I do have a couple of questions in terms of and again, these are going to be naive questions. But first off, I really would like to understand where do you fly this if for testing, and where is the competition?
We fly it for testing in St. Albans, Vermont, about 20 minutes from the Canadian border. And the competition is in Spaceport America in New Mexico.
Okay, because that goes to the differences in weather.
Yeah.
That would be very significant.
Yep.
Yeah.
We account for that in our simulations.
Yeah, I'm sure you are. I just am saying that, some of the issues you had with wet, or potential wet cardboard would be a Vermont issue and not an issue out in the desert.
Actually, that's a valid point, but we did integrate the motor at Tufts before, I think 2 days before. So
okay. And I just wondered, so St. Albans, I'm not exactly sure where that is in Vermont. I've been up to the Northeast Kingdom up there. But I guess what you're launching it into basically a treescape land, or is it farmland?
we actually go into Canadian airspace. No, sorry, no. It's farmland. It's farmland. There's a couple of square miles of basically nothingness. There's very few trees, which means recovering the rocket is a lot.
Yeah.
We also
heard the anecdote about it getting hung up in power lines, and I was nodding my head going, okay, that's what I was thinking about, is you can't possibly be doing this around Tufts because someone's going to get killed with that giant thing coming out of the sky like it is.
The power line thing was actually in Genesee, New York.
Oh, sure.
Yeah.
They could be anywhere.
Yeah.
and they're always right where you don't want them. But
yeah.
I also was wondering about that. I mean, I was very surprised, just because I'd never seen it before, that really long cable you have. It's, it's 3 stories at least. It's taller than my house by maybe a couple of times. It's quite a dangling piece you have there, and the observation on things tangling was very that is an important point. Tangling and cutting of the lines would be a disaster. So anything you can do on that, because that's not something you can simulate. That's just random bad luck.
So we actually we troubleshoot the tangling of the harness by reefing and coiling the harness beforehand and taping it with painter's tape, which also helps with the shock force of the deployment. So it has to break that tape before it comes out. And so there's only like probably 2 feet of harness actually not coiled inside of the
No, I wasn't worried about before deployment. I was worried about after deployment that you've got it flapping around up there and that something's going to do. It's not in the how you put it together and make sure it doesn't get tangled in the rocket. It's well, once you're coming down.
Right, well, every section of the airframe is, I think, greater than 5 pounds, so I'm not that concerned about the actual sections of the rocket getting like thrown around in the air, because the gravity will pretty much take care of and like throw tension, a lot of tension inside of the
Swivels on there
harnesses.
too, right?
We do have swivel links attached to the chutes so that they don't like get coiled too much. Not coiled. I don't
I
know.
also, I just a couple of quick ones. Again, these are naive questions, but I really liked your emphasis on test. I haven't done rocketry experiments, but I do space experiments, and we've always found that you actually can find a lot of your issues out through doing multiple tests. And I like your idea of using the shop vac. I was wondering if you could just do drop tests with subscale hardware, testing out, try to get it to,
We actually do plan to, I forgot to add this, but we do plan to like find a building and drop it from a building.
yeah, exactly.
That isn't a plan, but we haven't, I forgot to put it on.
When you say it, what are we
Yeah,
dropping?
Oh, God.
Oh, okay.
Under what chute?
I don't know, shoot,
Okay,
we'll figure it out later, but we're gonna like drop tests of like the av bay from like a building so we can test like the state machines more properly and stuff like that. Because otherwise, like, you're not gonna get good data to test it because you.
No, you're not going to get out the 2 changes, which is what you're after. But
Yeah.
you can fake some of that.
Yeah.
And anyway, I like your emphasis on testing. I thought that was that's a realistic thing. And then to echo Sam's comment on the burns aren't going to matter with any changes in the drag coefficient. The burns are almost irrelevant. The
That's
problem.
also why they make the chutes out of ripstop nylon, so they don't get worse.
Yeah, but that's the only other thing. That's what the rips are. The rips are crack initiation or ripping initiation sites, and if they're, if it's a rip, then it could propagate. If it's a circular hole, it's not going anywhere. So again, I think if you just kind of looked at them and made sure there wasn't the beginning of a crack, I think you're right about being able to just go ahead and not even bother any repair on that, I would think. But anyway, Sam knows more because he's actually done this.
I was just saying they may still want to do that because
it's cheap,
they
right?
have to get past the safety reviews, which aren't just me. So,
right, but not for the testing. For the testing, you should probably
for the testing, it'll be fine.
reuse the thing just because you don't want to bother messing up another one.
Exactly.
Yeah.
Oh yeah, that's a good call. I hadn't thought of that. That's fantastic.
Other than that, I mean, again, I am not an electronics expert, so I can't help you out with any of your questions there. But the risk assessment is something you have to do for these things, and you seem to have addressed most of those things. So I'm impressed with that.
Well, thank you. Do you have any other specific questions or?
No, not really. Not really. One other thing, you were talking about, when you had the drawings to manufacture things. You never know what's going to break. And so I'd have at least 1 and possibly 2 spare parts along, even though you never use them.
Fun story. There were a couple of parts that we made a couple spare parts for, and then all of the parts got lost. So it's definitely a good idea.
Yeah.
All right. Anyways, thank you guys both for coming to the CDR. Sam, thank you so much for all the incredibly helpful feedback. We'll be in contact if we have any further questions and we continue building stuff. And yeah, I'm so proud of the entire team for everything we've done. It's just
yeah, it really is good job.
Yeah, good work. Excellent test flight. It's great.
Yeah. That was the fact that it it worked. Like the first time I was so happy about that. All right, anyways, thank you. Enjoy the rest of your evening. And that is it for our second design review.
Thanks for staying the whole time, guys. I was only 2 hours.